Out in the frozen dark, a deep blue world hides more secrets than we have yet uncovered. This is Neptune, the solar system's final giant, a place of winds that scream at supersonic speeds and storms that vanish without a trace. It was first spotted not by chance, but through brilliant mathematical prediction in the mid-1800s. Since then, it has only revealed itself as a realm of profound mysteries. By the end of this journey, you will know 25 of its most baffling enigmas that are reshaping our understanding of the cosmos. We will explore how a planet so far from the Sun can rage with such violent weather, and why its largest moon is an alien trespasser from the deep. What does it feel like to stand at the very edge of our planetary knowledge? In 1989, Voyager 2 raced past Neptune and revealed a sight that stunned astronomers. A vast dark vortex larger than our own planet was churning in that deep blue atmosphere. This was the Great Dark Spot, a storm so immense it could swallow the Earth whole, a northern cousin to Jupiter's famous Great Red Spot. It was a colossal anti-cyclonic system, meaning it spun in the opposite direction of the planet's rotation, whipping clouds of frozen methane into a frenzy high above the main atmosphere. Scientists expected this titanic storm to persist for decades, perhaps even centuries, just as Jupiter's storm has. But Neptune had other plans. When the Hubble Space Telescope turned its gaze to the planet just a few years later, the unthinkable had occurred. The Great Dark Spot was simply gone. It had vanished without a trace, leaving astronomers to stare into a suddenly calm, featureless blue. This sudden disappearance is profoundly strange. Jupiter's Great Red Spot has been raging for at least 400 years, a near-permanent fixture in its sky. Yet on Neptune, a storm the size of a world can form and dissipate in what amounts to a cosmic blink of an eye. What does this tell us about the hidden forces at work in that frigid realm? The instability of Neptune's weather hints at an atmosphere driven by energy sources we are only beginning to comprehend, where the very rules of meteorology are rewritten in the cold of deep space. That vanishing storm points to a hidden engine of unimaginable power deep within the planet. Neptune is not merely a cold, distant world passively soaking up the faint warmth of the sun. It is a cosmic powerhouse radiating more than twice the energy it receives from our star. This internal furnace is the secret force behind those supersonic winds, a relentless blast of heat rising from the core to churn the atmosphere into a frenzy. Without it, Neptune would be a far calmer, almost dormant place. The question that haunts scientists is a simple one: where does all this heat come from? For a gas giant like Jupiter, the explanation is relatively straightforward. It is still slowly contracting under its own immense gravity, and that process of gravitational squeezing generates tremendous heat. But Neptune is much smaller and should have cooled off billions of years ago. Its continued feverish output defies all expectations. One compelling theory suggests it is raining diamonds deep inside the planet. Imagine an atmosphere rich with methane, where immense pressure breaks the molecules apart. The carbon atoms released from their bonds are squeezed together as they sink toward the core, crystallizing into a shower of solid diamonds. This slow, constant downpour of heavy gemstones releases gravitational energy as they fall, converting into the raw heat that drives the planetary engine. Another idea points to residual warmth left over from the planet's own violent birth, a primordial heat that has been trapped and slowly leaking out for 4.5 billion years. Yet none of these explanations fully account for the sheer intensity of the thermal energy we observe. This is not just a scientific curiosity, it is a fundamental mystery about how giant planets live and die. If we cannot understand the inner workings of our own solar system's final giant, what does that say about the countless ice giants we are now discovering around other stars? Neptune's hidden heat is only the beginning of its defiance. This world also possesses a magnetic field that behaves like nothing else in our solar system. While Earth's magnetic field is neatly aligned, with poles roughly corresponding to its geographic north and south, Neptune's is profoundly skewed. Its magnetic axis is tilted at a staggering 47 degrees from its axis of rotation. To put that in perspective, if Earth's magnetic field were tilted that much, your compass would point toward Florida instead of the North Pole. But the strangeness does not stop there. This tilted field is not even centered on the planet. It is offset from Neptune's core by a distance nearly half the planet's radius, creating what scientists call an offset dipole. This bizarre configuration makes the magnetic environment around Neptune wildly asymmetrical and unpredictable. The field's strength varies dramatically depending on where you are, and it tumbles through space in a complex, lopsided wobble as the planet rotates. This presents a fundamental challenge to our basic understanding of how planetary magnetic fields are born. The prevailing dynamo theory, which works well for Earth and Jupiter, suggests that a magnetic field is generated by the churning of molten, electrically conductive material in a planet's core. But Neptune's off-kilter, wandering field simply cannot be explained by a simple core dynamo. The evidence points to something far more unusual happening deep within its interior. Scientists now hypothesize that the magnetic field is not generated in the core at all, but in a vast, intermediate shell. This shell is thought to be composed of a bizarre, exotic substance known as superionic water mixed with ammonia. Under the extreme pressures inside Neptune, water molecules break apart. The oxygen atoms form a rigid crystalline lattice like the structure of a solid, while the hydrogen ions flow freely through it like a liquid metal. This creates an electrically conductive ocean, a slushy mantle that can generate a magnetic field, but one that is inherently unstable and prone to the extreme tilts and offsets we observe. This is not just a minor anomaly. It forces us to rewrite the textbook on planetary magnetism. Neptune reveals that the invisible forces shaping a world can emerge from layers we never knew could exist, turning our solar system's final giant into a laboratory for physics that defies imagination. This magnetic oddity is a prelude to a world even stranger, one that circles Neptune itself. The planet's largest moon, Triton, is a cosmic rebel that should not exist where it is. It travels around Neptune in the wrong direction, a retrograde orbit that defies the natural formation of the solar system. Every other large moon in our celestial neighborhood orbits its planet in the same direction the planet spins. Triton, in its stubborn backward path, is the sole exception. This single fact reveals its incredible origin story. Triton is not a native of the Neptunian system. It is a captured alien world, a colossal object that once roamed freely in the distant Kuiper belt beyond Pluto. By some cosmic chance, it strayed too close to Neptune's gravity and was ensnared, forced into its current backward dance. The violence of that capture event must have been catastrophic. It would have torn apart any pre-existing moons orbiting Neptune, shredding an entire original satellite system into the rings and debris we see today. But the strangeness of Triton only deepens when you look at its surface. This is not a dead, crater-scarred relic. It is one of the most geologically active worlds in our entire solar system. Its frozen plains, made of nitrogen and methane ice, are astonishingly young, resurfaced so recently that few impact craters remain. And from this icy crust, towering geysers erupt, spewing dark dust and nitrogen gas miles into its thin atmosphere. These are not volcanoes of fire, but cryovolcanoes of ice, driven by the warmth of the distant sun or by internal tidal forces. The presence of this ongoing activity points to a source of heat within Triton, and that leads to the most thrilling possibility of all. Scientists strongly suspect a global subsurface ocean of liquid water sloshes beneath its icy shell, kept from freezing by the constant gravitational kneading from Neptune. Where there is liquid water, there is at least the potential for life, even if only in microbial forms. This captured wanderer, a world from the solar system's frozen fringe, could be hiding a warm, watery sea. The mystery of Triton is a layered one. How did Neptune manage to capture such a massive object without destroying it? What is the true nature of the ocean that may lie beneath its crust? And could this alien moon, born in the deepest cold, now be a sanctuary for the first stirrings of life beyond Earth? These mysterious rings are not the brilliant hoops of Saturn. Instead, they are faint, dusty bands clinging to the planet, and one of them is fundamentally broken. The Adam's ring, the outermost and most prominent of these arcs, does not form a complete circle. Its material is gathered into 4 dense, isolated segments named courage, liberté, égalité, and fraternité. These are not just slight variations in density. They are distinct, bright clumps separated by near emptiness, as if someone took a string of pearls and snipped it into pieces, leaving the fragments to orbit in a line. The central mystery is why this material does not simply spread out. According to the basic laws of orbital motion, the countless tiny particles within each arc should naturally disperse, smearing the structure into a uniform, continuous ring within just a few short years. Yet these arcs have persisted for decades. Something invisible must be acting as a cosmic shepherd, corralling the dust and ice into these tight formations. The leading suspect is gravitational resonance. The small moon Galatea orbits just inside the Adam's ring, and its gravitational pull may create stable pockets like gravitational wells where the ring particles become trapped. As the particles orbit, Galatea's consistent tugs could prevent them from wandering away, effectively confining them to these specific arcs. It is a celestial dance where timing is everything. But there is a problem. The mathematics of this interaction are incredibly delicate, and many simulations suggest Galatea's influence alone may not be strong enough to hold the arcs together so perfectly. This failure of the primary theory points to another, even more intriguing possibility. There could be tiny, unseen moons hidden within the arcs themselves. These so-called shepherd moons, too small for our telescopes to detect, would orbit within the rings, their minuscule gravity sculpting and maintaining the sharp edges of the arcs from within. We are left with a celestial choice. Is the ring structure the work of a single moon's distant rhythm, or is it the product of a hidden family of miniature shepherds we have yet to lay eyes on? This puzzle of confinement challenges our understanding of orbital dynamics at its most fundamental level. Those broken rings circle a world of unimaginable violence. Neptune does not just have wind, it hosts a perpetual hurricane of supersonic fury, with sustained winds clocked at over 1,200 miles per hour. This is not a fleeting gust. It is the fastest, most relentless weather system known to exist anywhere in our solar system, a record that stands unchallenged even by Jupiter's own raging storms. The sheer scale of this power defies all logic. How can a planet so far from the Sun, receiving only a faint whisper of solar energy, generate atmospheric chaos that dwarfs anything on Earth or its warmer planetary cousins? The answer lies in the strange and efficient engine we have already glimpsed deep within the planet. Neptune's tremendous internal heat, that unexplained furnace radiating more than twice the energy it gets from the Sun, provides the primary power for this atmospheric violence. This heat rises from the core, creating immense temperature differences between the warmer lower layers and the frigid upper atmosphere. That thermal imbalance is the fundamental driver, forcing colossal convection currents to form, where vast plumes of hot gas surge upwards only to cool and sink back down in a planet-wide churn. But heat alone is not enough to explain such extreme speeds. The atmosphere itself offers almost no resistance, composed mostly of hydrogen and helium, with a trace of methane that gives the planet its iconic blue hue. This gaseous envelope is incredibly slick. There is very little friction to slow the winds down. Once set in motion by the planet's internal heat engine, these gales encounter so little drag that they can accelerate to velocities that would be physically impossible on a world with a more substantial, textured atmosphere like our own. Think of it like pushing a block of ice across a smooth sheet of glass versus shoving it through thick mud. On Neptune, the block of ice is the wind, and the glass is an atmosphere with staggeringly low friction. This combination of a powerful internal driver and an incredibly slippery medium creates the perfect conditions for a supersonic tempest. This forces us to completely rethink what an atmosphere can be. On Earth, our weather is a complex interplay of solar heating and planetary rotation. On Neptune, it is a demonstration of raw internal power, a storm born from within. The existence of such violent winds on an ice giant tells us that these distant worlds are not the cold, quiet outposts we once imagined. They are dynamic, energetic, and governed by a set of physical rules we are only beginning to decode. Even the planet's poles defy simple explanation. While Neptune's equator is locked in a deep freeze, its south pole is mysteriously warm, a thermal anomaly unlike anything found on Jupiter or Saturn. This polar region is about 10 degrees Celsius hotter than the rest of the planet, a significant difference in a world where average temperatures plunge to -215 degrees. This is Neptune's warm south pole, a localized hotspot that should not exist on a gas giant so far from the Sun. The primary suspect for this heating is a seasonal cycle of almost unimaginable length. Neptune takes 165 Earth years to complete a single orbit around the Sun, meaning each season lasts for more than 4 decades. For 40 straight years, one pole is tilted toward the Sun, basking in constant sunlight, while the other is plunged into an equally long winter of darkness. The South Pole was in the midst of its long summer when this warmth was detected. The constant solar radiation, faint as it is, appears to have a cumulative effect, slowly baking the polar atmosphere over decades. But this explanation, while logical, only deepens the mystery. How does the atmosphere trap and distribute this heat so effectively? On Earth, our atmosphere and oceans circulate warmth from the equator to the poles, smoothing out temperature extremes. Neptune's supersonic winds should, in theory, do the same thing, rapidly mixing that polar warmth across the entire planet and erasing any hot spot. The fact that a 10-degree temperature difference can persist suggests that Neptune's atmospheric circulation is far more complex than a simple global blender. There may be a vast, stable vortex locked over the pole, a high-pressure system that acts like a thermal cap, preventing the warm air from escaping and mixing with the colder surrounding atmosphere. This reveals a world with weather patterns operating on a timescale almost incomprehensible to human experience. A single season on Neptune is longer than most human lifetimes. The slow, deliberate bake of a polar summer and the gradual chilling of its winter are cycles that shape the planet's climate in ways we are only beginning to measure. What other long-term changes are occurring in that deep blue atmosphere? Changes that would be invisible to us during our brief glimpse. The warm pole is a testament to the patient, grand rhythm of a world where time itself moves differently. That warm pole is a localized oddity, but the darkness surrounding Neptune is a system-wide enigma. The planet's rings are almost invisible, not because they are not there, but because they are composed of some of the darkest material in our entire solar system. If you were to compare them to Saturn's brilliant, icy hoops, it would be like comparing a shadow to a spotlight. These faint, dusty bands reflect only a tiny fraction of the sunlight that hits them, making them a profound challenge to observe and understand. Their composition holds the key to this mystery. Unlike the pristine water ice that makes Saturn's rings shine so brightly, Neptune's rings are thought to be a grimy mixture of silicate dust and complex organic compounds. These are not clean, reflective particles. They are more like cosmic soot, darkened over eons by relentless bombardment from cosmic radiation. This space weathering process is relentless. High-energy particles striking the ring material break down the chemical structures, leaving behind a dark, carbon-rich residue that absorbs light instead of reflecting it. This suggests the rings could be incredibly ancient, their original bright ice long since transformed into a dull, dark coating. Yet there is a competing and equally compelling theory that points in the opposite direction. Perhaps the rings are not ancient at all, but are geologically young and transient features. In this view, they are not permanent structures but temporary collections of dust, constantly being replenished by a hidden source. The primary suspect for this replenishment is Neptune's family of small inner moons. These tiny, dark worlds are themselves constantly pelted by micrometeoroids, tiny specks of space dust. Each impact kicks up plumes of fresh, dark debris, a steady rain of material that continuously tops up the rings, preventing them from slowly dissipating away over time. This creates a fascinating paradox. Are we looking at an ancient ring system that has been permanently darkened by radiation, or a young one that is constantly being remade from fresh, dark dust? The answer could be both. The rings might exist in a fragile equilibrium where their darkness is a product of both their age and their constant renewal. This makes their current faintness a temporary state in a much longer cosmic cycle, a snapshot of a system in flux. The very dimness of these rings forces us to question their lifespan. Are we witnessing a fleeting cosmic moment or the final dark chapter of a structure that has lasted for billions of years? The absence of other large moons around Neptune is a silent testament to cosmic violence. While Jupiter and Saturn are each orbited by a full family of substantial native moons, Neptune stands almost alone, its gravitational domain dominated by the single, colossal trespasser Triton. This void is not an accident of formation. It is the likely scar of a catastrophic gravitational upheaval that reshaped the entire system. The prevailing theory is both simple and staggering. Before Triton arrived, Neptune probably possessed its own system of several large, regular moons, worlds that formed alongside the planet from the primordial disk of dust and gas. But when the rogue Kuiper belt object we now call Triton strayed too close, it plunged into this orderly arrangement like a bull in a cosmic china shop. The resulting gravitational chaos would have been apocalyptic. Some of the original moons may have been flung clear out of the Neptunian system, cast adrift into the interstellar dark. Others likely collided with one another, shattering into countless fragments. The debris from this demolition derby could have coalesced to form the chaotic collection of small, irregular inner moons we see today, like Proteus and its siblings. These surviving moons are the clues to this ancient disaster. Proteus, the largest of this inner group, is a dark, cratered world that looks more like a battered asteroid than a proper moon. Its irregular shape and heavily scarred surface speak to a violent history of impacts and disruptions. Even more telling is the strange, wild orbit of Nereid, another of Neptune's moons. Nereid follows a profoundly eccentric path, swinging from very close to Neptune to extremely far away in a single, lopsided loop. This is the kind of orbit you would expect from an object that was violently gravitationally perturbed, a moon that was either captured during the chaos or had its original circular orbit brutally stretched. The entire Neptunian system as we see it today is a celestial crime scene. Triton is the dominant suspect, sitting in its unnatural retrograde orbit, while the smaller moons are the scattered debris and traumatized survivors of the event. Their very existence, their shapes, and their paths all point to a single, shattering conclusion. We are looking at the aftermath of a planetary system's near total destruction, a ghostly remnant of what was lost when an alien world invaded. This leads to a profound question. What did that original native family of Neptunian moons look like before the cataclysm? Were there ocean worlds among them, or frozen landscapes with their own unique histories? We will never know, for their secrets were erased in a moment of gravitational terror, leaving behind only the cryptic clues held by the survivors. Amidst the dark vortices and supersonic winds, Voyager 2 spotted a fleeting, brilliant anomaly. Dubbed the Scooter, this bright white cloud was a high-speed enigma, a feature that moved with impossible velocity. It consistently completed a full lap around the planet roughly every 16 hours, outpacing even Neptune's own rapid rotation. This meant the Scooter was not merely being carried by the wind, it was actively racing ahead of the planet's spin, a true atmospheric speedster. Its nickname perfectly captured its swift, darting motion against the slower, deeper blue backdrop. So what was this fleeting phenomenon? Scientists believe it was likely a massive convective cloud tower, a colossal plume of warm gas erupting from the lower atmosphere and soaring high into the stratosphere. At that extreme altitude, with far less atmospheric drag, it could surf the powerful jet streams, achieving those incredible speeds. Alternatively, it might not have been a cloud at all, but a vast hole torn in the deeper, darker cloud decks. A clearing that revealed a brighter, whiter cloud layer far below, creating the illusion of a fast-moving bright spot scooting across the planet's face. The greatest mystery, however, is why we have not seen it since. The Scooter was a transient feature, here one moment and gone the next. Later observations by the Hubble Space Telescope failed to find any consistent, recurring phenomenon matching its description. This suggests that the Scooter was not a permanent fixture, but a rare and violent atmospheric event. A sudden, powerful upwelling of energy from the planet's hidden furnace that briefly punched through the upper atmosphere before dissipating back into the churning blue. Its fleeting existence reminds us that Neptune's atmosphere is a place of constant, dramatic change, where colossal features can appear and vanish not over centuries but over a handful of Earth years. The Scooter offers a tantalizing glimpse into the most dynamic and unpredictable weather in the solar system, a ghost in the machine that we witnessed only once. This strange imbalance in Neptune's weather suggests a deeper, more systemic mystery. When we observe the planet, we see a clear and puzzling preference for storm formation and cloud activity in its southern hemisphere. It is as if the entire southern half of the planet is inherently more turbulent, a permanent tempest compared to the relative calm of the north. But is this a true, lasting feature of Neptune, or are we simply seeing a fleeting snapshot in a planetary cycle that spans centuries? With our limited window of observation, it is difficult to say for certain. The key to this puzzle likely lies with Neptune's extreme axial tilt. The planet leans over at a dramatic 28 degrees, very similar to Earth's own tilt. This means Neptune experiences pronounced seasons just as we do, but on a timescale almost beyond human comprehension. Each season on this blue giant lasts for over 40 Earth years. For 4 straight decades, one hemisphere is bathed in constant, though faint, sunlight, while the other is locked in an equally long, deep freeze of a winter. The southern hemisphere was in the height of its long summer when Voyager 2 flew by and when many of our most detailed Hubble observations were made. That sustained solar energy, even from a distant sun, could be the engine driving the enhanced cloud formation and storm activity we have witnessed. It would create a significant temperature difference between the simmering summer hemisphere and the frigid winter one, powering colossal convection currents and fueling the southern tempests. Yet this seasonal explanation, while elegant, may be too simple. Why would the weather not simply flip when the seasons change? Should we not expect the northern hemisphere to become the dominant storm center when its own summer arrives? Our models predict this should happen, but we have not been observing Neptune long enough to witness a full seasonal transition. We are like someone who has only seen a single hour of a 4-decade-long play, trying to guess the entire plot. There may be other, more permanent factors at work. Perhaps the internal heat flow from the planet's core is not distributed evenly, welling up more powerfully in the south. Or maybe the complex chemistry of the atmosphere itself differs between the hemispheres, creating conditions more ripe for cloud formation on one side of the world than the other. This mystery of asymmetry cannot be solved with a single observation. It demands a patient, long-term vigil, a cosmic watch that spans generations. We must wait and see if the stormy south eventually quietens, and if the north awakens with its own fury, or if this lopsided world will forever keep one face more turbulent than the other. Deep beneath the raging winds and dark vortices lies the planet's true heart of darkness, a mantle of almost unimaginable strangeness. This is not a layer of rock or a sea of magma, but a vast, deep ocean of exotic ices. We use the word ice here not in its familiar sense, but to describe a state of matter under such extreme pressure and temperature that water, ammonia, and methane are squeezed into forms that defy all earthly experience. This immense shell, making up the bulk of Neptune's interior, is the source of its greatest mysteries. Here, the rules of chemistry and physics are rewritten. Water, the substance of life, transforms into something entirely alien. Under pressures over 1 million times greater than Earth's atmosphere and temperatures reaching thousands of degrees, water enters a phase known as superionic water. In this bizarre state, the very molecules we know as H2O are torn apart. The oxygen atoms are forced into a rigid, crystalline lattice like the structure of a solid metal. Meanwhile, the hydrogen ions are stripped away, becoming a fluid that flows freely through this oxygen cage like a swarm of charged particles. This creates a substance that is simultaneously a solid and a liquid, a crystalline ocean that can conduct electricity with the efficiency of a metal. This superionic water is the hidden engine behind Neptune's greatest anomalies. Its electrical conductivity is the key to generating the planet's profoundly skewed and offset magnetic field. The churning motions within this slushy, conductive mantle, driven by the planet's internal heat and rotation, act as a colossal dynamo. But because this dynamo is not centered in a molten core, but is instead spread throughout a vast, unstable shell, it produces a magnetic field that is intrinsically lopsided and prone to wild tilts. This exotic mantle also governs the flow of the planet's internal heat. The constant movement of hydrogen ions through the solid oxygen lattice transfers thermal energy with incredible efficiency, helping to ferry that mysterious excess warmth from the deep interior up toward the atmosphere. This process may be a primary reason why Neptune's internal furnace burns so brightly billions of years after its formation. Yet for all our theoretical understanding, superionic water remains a hypothetical state. We cannot recreate its exact conditions in any laboratory on Earth. Our most powerful presses can only hint at its properties, leaving its true behavior as one of the great unproven frontiers of planetary science. We are left to infer the nature of this hidden ocean from its effects on the world above, trying to understand a form of matter that is, for now, more a prediction of quantum mechanics than a substance we can hold and study. The mantle of Neptune is a realm of pure theory, a ghostly ocean of crystalline water that may hold the final keys to understanding the solar system's last giant. This brief existence of its great storms sets Neptune apart from every other giant in our solar system. While Jupiter's great red spot has raged for centuries, Neptune's colossal dark spots appear, dominate the weather for a few years, and then simply fade away. Why do these planetary-scale hurricanes, powerful enough to swallow our world, lose their energy so swiftly? The answer seems to lie in the very nature of this ice giant, a world without an anchor. On Earth, a hurricane derives energy from warm ocean waters but eventually weakens when it moves over land, its fury broken by the friction of a solid surface. Neptune has no such surface. Its atmosphere simply transitions gradually into a superheated, slushy interior. Without a continental landmass to disrupt its flow, a storm on Neptune might be expected to rage forever. Yet the opposite is true. This lack of a solid ground may be the very reason for its storm's short lives. With nothing to grind against, the storm has no stabilizing force. It is a free-floating vortex in an impossibly slippery medium, vulnerable to being torn apart by its own environment. The planet's supersonic zonal winds, those vast rivers of gas flowing at different latitudes, act like cosmic shear forces, constantly straining the storm's structure. Imagine a spinning eddy in a river being pulled in two different directions by faster currents above and below it. That is the fate of a Neptunian storm, stretched and shredded by the relentless winds that surround it. Furthermore, these storms may be starved from within. A hurricane on Earth is a heat engine powered by the temperature difference between the warm ocean and the cool upper atmosphere. On Neptune, the internal heat rising from the core might initially fuel a storm, but that energy source could be inconsistent or simply not focused enough to sustain such a massive vortex for long. The storm forms, churns through the available energy, and then dissipates, its components scattered back into the churning blue atmosphere. This reveals a fundamental difference between a gas giant and an ice giant. Jupiter's storms are deep-rooted, potentially tapping into immense energy reservoirs far below. Neptune's dark spots might be shallower phenomena, brilliant but fleeting disturbances in the upper cloud decks, lacking the deep foundation needed for longevity. The fleeting nature of its greatest storms paints Neptune not as a world of permanent features, but as a canvas of temporary, violent art, where masterpieces of meteorological fury are created only to be erased by the very forces that gave them life. Nereid's wild path is a permanent record of that ancient chaos. This moon, Neptune's third largest, follows one of the most lopsided orbits known to science, a dizzying loop that defies the neat, circular paths of most other large satellites. At its closest approach, Nereid swings to within 1.3 million kilometers of Neptune, only to be flung out to a staggering distance of 9.6 million kilometers at its farthest point. This is not a gentle ellipse, it is a cosmic roller coaster, a trajectory so extreme it suggests the moon was thrown about by an almost unimaginable force. The prime suspect for this violence remains the capture of Triton. If Nereid was one of Neptune's original native moons, the arrival of the colossal interloper would have sent gravitational shockwaves through the entire system. Nereid could have received a colossal gravitational kick, a slingshot effect that stretched its once tidy circular orbit into the wildly eccentric path we observe today. It would be a survivor, a primordial moon permanently scarred by the invasion. Yet there is another, equally compelling possibility. Perhaps Nereid is not a native at all, but another captured object. In this scenario, it was a free-floating denizen of the Kuiper belt that was snared by Neptune's gravity during the same chaotic period. Its extreme orbit would then be a natural result of that capture process, a path it has followed ever since it was imprisoned. This leaves us with a fundamental question about identity. Is Nereid a traumatized original, its orbit a testament to a system shattered? Or is it a fellow captive, another piece of cosmic debris ensnared in the same event that brought Triton to heel? Its chaotic dance is a clue written in gravity, a permanent reminder that the calm we see today is only a fragile peace following a celestial war. This persistent bright eye staring out from the deep blue haze was not seen by Voyager. It is a feature of the modern Neptune, a high-altitude storm system so stable that astronomers have nicknamed it the Wizard's Eye. Unlike the fleeting Great Dark Spot or the transient Scooter, this compact, brilliant cloud has endured for years, a constant and glaring anomaly in the planet's southern hemisphere. Its longevity is its greatest mystery. How can one storm system remain so coherent while others around it form and dissipate with such rapidity? The answer may lie in its altitude. The Wizard's Eye is not a deep atmospheric vortex like the vanished dark spots. Instead, it appears to be a colossal convective storm, a towering pillar of upwelling gas that has punched its way into the highest, coldest layers of the stratosphere. There, it forms a vast canopy of bright, fresh methane ice crystals that reflect the distant sun's light with startling intensity. Its stability suggests it is anchored by something powerful below, perhaps a consistent and vigorous upwelling of warmth from the planet's hidden interior, a fixed hotspot on which this brilliant cloud sits like a crown. This endurance forces us to consider a new class of Neptunian weather. We may be looking at a polar cyclone, a vast, stable vortex locked over the South Pole, similar to the hurricanes we sometimes see at Earth's poles but on a monstrous planet-spanning scale. Or it could be a standing wave, a permanent atmospheric feature generated by the flow of wind over a massive subterranean structure, like a mountain range of solid diamond deep within the planet's slushy mantle. The Wizard's Eye does not behave like the other, more transient storms. It is a landmark, not a wanderer. Its very existence suggests that Neptune's atmosphere, for all its chaos, possesses hidden points of stability that we are only now beginning to map. What other permanent features might be hiding in that churning blue, waiting for a patient observer to notice their steady, silent presence? That enduring Wizard's Eye highlights just how much we still have to learn from this distant world. Yet the greatest mystery surrounding Neptune might not be on its surface, but in our own reluctance to return. For more than 3 decades, our only close-up look was that single, hurried flyby from Voyager 2 in 1989. Since then, we have sent orbiters to study Jupiter and Saturn in stunning detail, mapping their moons and decoding their atmospheres for years on end. But Neptune, the solar system's final giant, has been left in the dark, a world we observed from an immense distance. This absence of a dedicated mission is a profound puzzle in itself. Why has this magnificent blue world been so neglected? The answer lies in a web of immense technical and financial challenges. Reaching Neptune requires a spacecraft to undertake a journey of staggering length, a voyage that would take over a decade even with the most powerful rockets and strategic gravity assists. Once there, the spacecraft would need to carry enough fuel to slow down dramatically, to break from a solar system crossing speed into a stable orbit around the planet. This orbital insertion maneuver is a feat of precision engineering that demands a tremendous amount of propellant, adding immense weight and complexity to the entire mission. And then there is the problem of power. At Neptune's distance, the Sun is reduced to little more than a bright star. Solar panels, which work so well for missions to Mars or Jupiter, become virtually useless, unable to gather enough light to power the spacecraft's instruments and transmitters. A Neptunian orbiter would have to rely on nuclear power, using the heat from radioactive plutonium to generate electricity. These generators are expensive, politically complex, and in limited supply. All of these factors combine to make a dedicated Neptune mission one of the most ambitious and costly endeavors we could possibly undertake in planetary science. The result is a massive data gap that leaves us with more questions than answers. We are forced to piece together the story of this dynamic, violent world from a handful of Voyager images and the blurry glimpses provided by telescopes like Hubble. It is like trying to understand an entire novel by reading a single, randomly selected page every few years. This lack of continuous observation means we have missed entire chapters in Neptune's life. We do not know how its strange magnetic field fluctuates over time. We cannot say for certain if the Wizard's Eye is a permanent fixture or will one day vanish. We have no idea what secrets lie on the night sides of its bizarre moons. This informational void transforms Neptune into a different kind of mystery, one defined not by what we have found, but by everything we have yet to see. Neptune's own discovery was a triumph of celestial prediction, found not by accident but by tracing the subtle gravitational tugs it exerted on its neighbor, Uranus. Now, history may be repeating itself, with Neptune's own motion at the center of the mystery. Astronomers have detected faint, unexplained wobbles in Neptune's orbit, tiny irregularities that suggest something massive, something unseen, is pulling at it from the dark frontiers beyond. This is the speculative but compelling case for Planet X, a hypothetical world several times more massive than Earth, lurking in the frozen vastness of our outer solar system. The evidence is not in Neptune's path alone, but also in the strange, clustered orbits of small, icy bodies in the distant Kuiper belt. These objects swing around the Sun in aligned, tilted paths that seem statistically impossible unless a large planet's gravity is herding them. It is a ghostly signature, a pattern in the chaos that points toward a hidden architect. The hunt for this world is a direct echo of the 19th century, when Urbain Le Verrier and John Couch Adams calculated the position of an unknown planet based solely on its gravitational influence. Their work led directly to the telescope that found Neptune. Today, we are in a similar position, using the most powerful telescopes on Earth and in space to scan the predicted orbital path of this potential ninth planet. Confirming its existence would be one of the greatest astronomical discoveries in a century, rewriting the map of our own cosmic backyard. Yet denying its existence would be just as profound, forcing us to find another explanation for the strange alignments and perturbations we see. Is Neptune's subtle dance the key that will unlock the final major planet in our solar system? Or is it merely revealing yet another, even stranger, gravitational puzzle we have yet to comprehend? Even the color of this distant world holds a secret. Neptune's deep blue hue comes from the methane in its atmosphere, a gas that absorbs red light and reflects blue. But that absorption is not constant. It flickers. Scientists have detected subtle, yet significant, changes in how strongly Neptune's atmosphere soaks up sunlight in specific methane bands, and these shifts appear to sync with the planet's unimaginably long seasons. For decades at a time, as one hemisphere endures its 40-year summer, the methane signature seems to strengthen or weaken in a slow, rhythmic dance. What could possibly be causing this atmospheric heartbeat? One possibility is that the actual amount of methane in the upper atmosphere is changing. Perhaps the long polar summer warms the atmosphere just enough to release more methane from lower, hidden reservoirs, causing a seasonal surge in the gas that deepens the blue. Or the change might not be in the gas itself, but in a veil that lies above it. High-altitude haze layers composed of complex hydrocarbons created when sunlight breaks methane apart could be the true culprits. During a hemisphere's long summer, increased solar radiation might cook up thicker, more extensive hazes. These layers would act like a screen, altering how we perceive the methane absorption from afar, making it appear stronger or weaker without the gas itself changing at all. A third, and perhaps most intriguing, idea involves the planet's violent weather. Neptune's supersonic winds are the engine of its global circulation, a complex system of upwelling and sinking air that could be shifting with the seasons. A change in circulation might dredge up air with different chemical compositions from the deep, or simply redistribute the existing methane and hazes in new patterns, concentrating them in some areas and thinning them out in others. Pinpointing the true driver is not just an academic exercise. It is absolutely crucial for building accurate climate models for all ice giants. These faint, rhythmic changes in methane are the planet's way of whispering to us about the powerful, slow-moving forces that control its climate. If we can learn to decode this whisper, we will not only understand Neptune better, but we will be able to predict the behavior of the thousands of similar ice giants orbiting other stars. This subtle mystery of light and gas is a key to unlocking the very nature of worlds at the edge of darkness. Neptune's enduring heat is a direct challenge to the story of its birth. Our best models for planetary formation paint a specific picture of how an ice giant should have cooled over time, and Neptune stubbornly refuses to follow the script. These models suggest that planets like Neptune formed from the slow, gentle accretion of icy planetesimals in the outer solar system, a process that would have created a world with a relatively uniform, layered interior. According to this classic view, the immense heat from that violent formation period should have radiated away into space over the last 4.5 billion years, leaving behind a cold, quiescent world. Yet Neptune blazes with internal energy, a clear sign that its history was anything but calm and orderly. The planet we see today is an thermal anomaly, an object that has retained a youthful fever long into its old age. This forces a radical rethink of its entire life story. The leading revision points to a dramatic and chaotic childhood for our solar system, a time of planetary pinball. In this new narrative, Neptune did not form where it currently resides. It was born much closer to the Sun, in a region richer with material, before gravitational interactions with Jupiter and Saturn flung it outward into the cold darkness. This grand migration would have been a profoundly violent event. As Neptune journeyed outward, its gravity would have stirred up the primordial Kuiper belt, scattering countless icy bodies inward. Some of these planetesimals, some as large as small moons, would have slammed into the young Neptune at tremendous speeds. Each colossal impact would have delivered a massive injection of energy, like striking a bell with a hammer, reheating the planet's interior to a white-hot fury. This bombardment of icy comets and dwarf planets may have done more than just deliver heat. It could have fundamentally scrambled the planet's internal composition, churning its layers and depositing fresh, volatile, rich material deep into its mantle. This would have altered its very chemical makeup, creating the conditions for the exotic, superionic water oceans we now suspect exist. The planet's current heat flow, then, might not be a simple leftover from its formation. It could be the complex legacy of this violent migration, a combination of primordial heat, impact energy, and the slow, ongoing release of gravitational potential energy as denser materials like diamond continue to rain toward the core. Our models struggle because they assume a peaceful, isolated formation. Neptune reveals a truth that is far more interesting, a history written in collisions and gravitational turmoil, leaving us with a world that defies our simplest expectations of how a planet should live and cool. The very ice that coats Triton's surface holds the secret to its explosive activity. Voyager 2's cameras captured something no one had ever seen before on a world so distant, dark plumes rising several kilometers from the moon's frozen south polar cap. These were not eruptions of molten rock, but geysers of nitrogen gas, blasting dust into a sky 10,000 times thinner than the air on Earth. The driving force behind this alien spectacle is as ingenious as it is strange, a phenomenon known as the solid-state greenhouse effect. Picture a layer of transparent nitrogen ice, as clear as a window pane, sitting atop a darker, sun-absorbing layer of material. The weak sunlight at this distance is still enough to pass right through the clear ice, but when it hits the dark layer underneath, that energy is trapped as heat. This warmth does not melt the nitrogen ice, it causes it to sublimate, transforming directly from a solid into a gas. Trapped beneath the icy ceiling, this nitrogen gas builds pressure relentlessly until it finally fractures the surface, exploding upwards in a violent jet that carries the dark dust with it into the void. We see the result as those towering, dark plumes, a sign of a world breathing its frozen atmosphere. Yet for all the elegance of this theory, crucial pieces of the puzzle are missing. The exact nature of the dark material that absorbs the sunlight remains unknown. Is it complex organic compounds created over eons by radiation hitting the ice, or is it silicate dust from deeper within the moon? Furthermore, what is the precise trigger for the eruption? Does the gas seek out pre-existing cracks and weaknesses, or does the pressure build until it creates its own explosive exit? These geysers are more than just a stunning visual display. They are a primary engine for Triton's entire atmosphere. Each eruption replenishes the thin veil of gases that would otherwise escape into space or freeze back onto the surface. This creates a dynamic and ever-changing climate on a scale we are only beginning to understand. A cycle of ice, gas, and dust driven by the faint whisper of a faraway sun. What other frozen worlds, both in our solar system and beyond, might share this same silent, explosive breath? The faint, fragmented arcs of Neptune's rings are held in place by an invisible hand. We have strong reason to believe that a hidden population of tiny, unseen moons are the cosmic shepherds for these strange formations. These moonlets, likely no larger than a few miles across, would orbit within the rings themselves, their minuscule gravity creating order within the chaos. Each small moon's gravitational pull would nudge nearby ring particles, creating a narrow zone of stability and preventing the dust and ice from drifting away. Without these unseen shepherds, the delicate arcs of courage, liberté, égalité, and fraternité should have smeared into a uniform, featureless band long ago. The primary challenge is that these moonlets are simply too small and dark to be seen from our vantage point. They are lost in the overwhelming glare of Neptune itself, faint specks of rock and ice hiding in the shadow of a giant. Our most powerful telescopes, even Hubble, struggle to pick out such dim objects from a distance of nearly 3 billion kilometers. A future orbiter mission, equipped with sensitive cameras designed to peer into the glare, would almost certainly reveal a hidden celestial metropolis. It would find not just one or two, but perhaps dozens of these tiny shepherds, each one a testament to the complex gravitational ballet that sculpts the rings. Discovering this hidden population would do more than just solve the puzzle of the arcs. It would reveal the final pieces of the Neptunian system's architecture, showing us a miniature solar system in its own right, where worlds the size of cities govern the flow of dust and ice. The silence from that dark frontier may not be emptiness at all, but the quiet presence of countless small sentinels holding the line against the relentless pull of gravity and time. This world operates on a timescale almost beyond human comprehension, and that is the source of its next great mystery. We have witnessed less than a single Neptunian year since its discovery in 1846, a mere sliver of its 165 Earth-year orbit. Our entire history of detailed observation spans just a fraction of one long, slow summer in its southern hemisphere. We have no complete baseline, no way of knowing what a full seasonal cycle truly looks like on this distant blue giant. Recent findings have only deepened this enigma. As Neptune's southern hemisphere approached its summer solstice, a point where we expected the atmosphere to be at its warmest after decades of constant sunlight, something bizarre happened. Instead of warming, the planet's global temperature plummeted. Over a 17-year period, astronomers documented a stunning drop of about 8 degrees Celsius across the entire stratosphere. This was followed by a dramatic warming spike at the South Pole, a localized fever in the middle of this unexpected global chill. This behavior is the complete opposite of what any of our climate models predicted. It is as if we watched for summer to arrive and instead were met with an unanticipated deep freeze. What colossal forces are at play that can override the faint warmth of the sun and cause such a large-scale temperature reversal? The answer may lie in the complex chemistry of Neptune's upper atmosphere. The slow, seasonal formation of haze particles could be responsible. As sunlight increases during a hemisphere's long summer, it might trigger a photochemical reaction, creating a blanket of hydrocarbon hazes high above the clouds. This global shroud could act like a planetary sunshade, reflecting solar energy back into space before it can heat the layers below, leading to the observed global cooling. Meanwhile, the sudden polar warming could be a completely separate phenomenon, a massive storm system churning up heat from the deep interior and unleashing it at the pole. This reveals a climate system of staggering complexity, where solar heating, internal furnace heat, and atmospheric chemistry are locked in a constant, slow-motion battle for control. We are left staring at a clock whose face we can see, but whose inner workings are a complete enigma. To truly understand the climate of Neptune, we would need to watch it for centuries to see how it breathes and changes over multiple of its own years. Until then, its long-term rhythms remain one of the solar system's best-kept secrets. deep within that churning atmosphere of methane lies the raw material for one of the most fantastical weather systems imaginable. The hypothesis of diamond rain proposes that inside Neptune, carbon atoms are crushed into glittering gemstones that fall perpetually through the dark. This process begins with the very methane that gives the planet its beautiful blue color. As you descend through the atmosphere, the pressure becomes unbearable, millions of times greater than anything on Earth. This incredible force literally squeezes the methane molecules until they shatter, breaking apart and releasing their constituent atoms. The lightweight hydrogen escapes upwards, while the heavier carbon atoms continue their relentless journey down into the hellish depths. In this environment of immense pressure and scorching temperatures, the carbon atoms are forced together, their atomic structure rearranging into the rigid, crystalline pattern of diamond. These newly formed diamonds, likely no larger than specks of sand or perhaps even pebbles, begin to sink. They are so dense that they fall through the slushy mantle of exotic ices, a slow, constant shower of solid gems descending toward the planetary core. Scientists have actually recreated a miniature version of this phenomenon in laboratories here on Earth. Using powerful lasers or diamond anvil cells, they subject samples of carbon-rich materials like polystyrene to sudden, immense pressure, mimicking the conditions inside these giant planets. In these experiments, they have observed the formation of tiny diamond-like structures, proving that the fundamental physics is sound. The ongoing debate is not about whether this can happen, but about the scale and the final fate of this cosmic treasure. Some models suggest the diamonds only fall a short distance before the increasing heat and pressure vaporize them back into carbon, creating a continuous cycle of creation and destruction. Others propose they sink all the way to the core, accumulating over billions of years into a layer of solid diamond hundreds of miles thick. This is more than just a poetic image. If this diamond rain is real, it solves a fundamental mystery about Neptune. As the heavy diamonds sink, they release gravitational energy which converts directly into heat. This slow, constant downpour could be a primary source of fuel for the planet's inexplicable internal furnace, driving the supersonic winds that scream across its surface. The entire planet could be powered in part by a silent, glittering storm raging deep within its heart. Even the length of a day on Neptune is a profound mystery. For a rocky world like Earth, measuring the rotation is simple. We just track a mountain or a crater as it spins back into view. But a gas giant has no solid surface, no permanent feature to follow. Its outer layers are a swirling, supersonic fluid, moving at different speeds than the planet's hidden core. To solve this, scientists turn to a different kind of signal, the rhythmic pulse of the planet itself. When Voyager 2 flew past, it detected powerful bursts of radio waves crackling from Neptune's skewed magnetic field. These emissions are thought to be tied to the rotation of the planet's deep interior, the only stable clock in a world of chaos. By timing the interval between these radio pulses, Voyager gave us our first reliable Neptunian day, 16.11 hours, yet this number refused to stay constant. Later observations from Earth revealed that the period of these radio emissions was not a perfect, steady tick. It fluctuates, changing by small but significant amounts over time. This is deeply strange. A planet's rotation, driven by the conservation of angular momentum from its formation, should be one of the most stable things about it. The fact that Neptune's radio heartbeat speeds up and slows down means we are not listening to the spin of a solid body. We are hearing the complex and unstable rhythm of its magnetic field, a field generated in that bizarre shell of superionic water. The fluctuations are a direct window into the turbulent interior. They reveal a fundamental disconnect between the outer atmosphere, which we see, and the deep, slushy mantle that powers the magnetism. The churning motions within that conductive ocean are not perfectly synchronized, great currents of electrically charged slush may speed up or slow down, creating pockets of stronger or weaker magnetic activity that manifest as a changing radio pulse. This means the very definition of a day on Neptune is fluid. Its rotation is not a single number, but a conversation between its deep internal engine and the lopsided magnetic field it creates. How do you measure time on a world where time itself seems to waver? This slow inward spiral seals the ultimate fate of the captured wanderer. Triton is trapped in a gravitational dance with Neptune that is slowly, inexorably tightening. Its retrograde orbit acts as a brake, and with every loop, the immense tidal forces from the planet's gravity sap a tiny amount of the Moon's orbital energy. The result is a decay so gradual it is almost imperceptible, a cosmic countdown measured in billions of years. The Moon is falling, and its final destination is a profound mystery. Two spectacularly violent outcomes are possible, and we cannot yet say which path this celestial drama will take. The first is a slow, cosmic unraveling. As Triton ventures closer to Neptune, it will cross a critical boundary known as the Roche limit. This is the point where the planet's gravitational pull becomes stronger than the Moon's own gravity. Triton will not be pulled apart in a single, explosive event. Instead, it will be systematically shredded, its icy crust and rocky core stretched and torn into a river of rubble. The result would be the most magnificent ring system our solar system has ever seen, a brilliant, wide belt of ice and rock circling Neptune, a final, glittering monument to the Moon that once was. The other possibility is a far more direct and catastrophic collision. If Triton's inward spiral remains stable enough to carry it through the Roche limit intact, it would be on an unavoidable collision course with the giant planet. The impact would be an event of almost unimaginable violence, releasing more energy than the detonation of every nuclear weapon on Earth 1 billion times over. It would rip open Neptune's atmosphere, scarring its deep blue face with a temporary, blazing wound that would be visible across the solar system. The physics governing this slow-motion fate are incredibly complex. The precise timeline, whether this happens in 100 million years or 10 billion, depends on the exact internal structure of both Triton and Neptune. Is Triton's interior rigid or slushy? How much energy is dissipated as heat within its subsurface ocean during each tidal flex? These unknowns make the countdown a variable we cannot yet pin down. We are left to contemplate a finale that will play out in the far future, a destiny written in the silent, patient mathematics of gravity that we can calculate but will never see. Each of these 25 mysteries, from its vanishing storms and supersonic winds to the diamond rain deep within its heart, paints Neptune not as a static world, but as a dynamic, evolving puzzle. We grapple with its skewed magnetic field, the alien origin of its moon Triton, and the faint, broken arcs of its rings held together by forces we cannot see. We are confounded by its unexplained internal heat, its warm pole, and the fleeting appearances of features like the scooter and the enduring wizard's eye. The very length of its day remains uncertain. Its climate operates on a timescale we have barely begun to measure, and the entire system stands as a ghostly testament to a violent, ancient upheaval. Every strange phenomenon, every unanswered question reveals a fundamental truth. The ice giants at the edge of our solar system are not simple, frozen relics. They are a class of planet governed by physics we are only starting to comprehend, a frontier of planetary science filled with exotic matter and unimaginable weather. Our current knowledge is merely a glimpse, a single page in a story that spans billions of years. The journey to understanding Neptune has just begun. To turn these mysteries into discoveries, we must keep looking. Follow the revelations from powerful new eyes on the cosmos like the James Webb Space Telescope, which is already peering into Neptune's atmosphere with unprecedented clarity. Support the scientists and engineers dreaming of the next great mission, an orbiter that could spend years unraveling the secrets of this deep blue world. Our solar system's final giant holds the keys to rewriting the story of how planets form and live. It is a reminder that the greatest adventures in exploration still lie ahead, waiting in the dark at the very edge of the light.